or concerns or ideas, please let me know. So we're gonna continue working with samples, the groups of data, and today's plan is to discuss what's in the middle, so-called median for the sample. So I will be, I guess, working with the same exact samples again that ones we're already familiar with. In fact, it doesn't really matter which samples you want to consider, the process will be pretty much the same. So if I take a look at the exercise 2 and try to rearrange these 6 times 2, 12 elements. So if I have 12 pieces of data, from the smallest to the largest in order. So the smallest here I have is 70.9, and then I can move to the larger and so forth. So the next will be 74, and then 78.6. So let me write it down. 74, 78.6. Turns out it's very important to prepare the sample to see what element will be in the middle. 79.5, 79.2. Because otherwise you can reshuffle your elements and put just any element in the middle, but I want to find a median, which is the middle element with respect to arrangement from the smallest to the largest. So it looks like I'm done with 70s. Next will be 80, 80.2, 82.5. So this is taking time, right? Well, this work needs to be done to find the middle element or the median. And the good thing is we don't have many elements in here, so we're almost there. So 83.7, 84.3. Okay. Almost done. And we also have 2 more, right? So 84.6, 85.3. 84. Of course, the computer will definitely do this much faster, but well, I guess we're done pretty much. So it's a good news. So the largest 86.2. So my 12 elements from the sample they gave us in the exercise 2 were rearranged. And if I want to take a half of these elements, so I take 0.5 times 12, I will produce 6. So first 6 elements, if I consider, will give me a first half of the sample. 2, 4, 6, like that. And then the other half, another 6 elements is here. So what should be in the center? What should be in the middle? The element called median. Well, I need to actually take the average of my 2 elements in the center. So 80.2 I need to add with 82.5 and divide this sum by 2. Take the average, 82.5, and divide it by 2. That's how we need to find whatever should be in the center, whatever is in the middle. And if you're not sure, you can always use a calculator to not make little mistakes. So I take scientific calculator, scientific. And then we'll just calculate. I think I didn't click Desmos, I clicked something else. Scientific, here it is. First choice, right? So they all work. If you like some other calculator, you have preference for something else, you can use anything you like. But I will always use the same to be consistent. So 82.5, and then put in the parentheses to make sure it's divided by 2. So 81.35 is what is median element for this particular group of elements, middle element. 50%, the half, was found. Well, median is here, and then we need to, well, we can use analogous procedure to find the other interesting things, such as a first quartile, first quarter of elements. So if I decide to split the group of 6 elements in 2 pieces here and find the first quarter, which is going to be 25% of my sample size, which is 12. Take a quarter, and looks like it's exactly equal to 3, right? So 3, so I need to go in the middle, in between of those 2 elements that sit in the center, analogously to the median findings. So it's 78.6, but I will add with 79.2. So this is my procedure for that. And when I 79. So just take the calculator again. I know you can do it without a calculator, but why bother? You can use technology for that. So what is that? 78.6. Add with 79.2. And then if you divide the sum by 2, the average is 78.9. Okay. First quarter, very similar way, you found 78.9. Quartiles. People say it's a first quartile, and similarly, we can find the quartile number 3, because if you want to look at the 3 quarters, Q3, I will also get this 3 quarters, or 75% of my sample elements of 12, and this will be 9. Okay? So it looks like it's 9. You can check it with a calculator if you want. And looks like analogously to the previous calculation, so average whatever sits on the place 9, 84.3, with the following place, which is 84.6. Right? This is interesting, right? Interesting procedure. So it's probably going to be like 84.45, something like that. I think like 45. But of course, you can double check it just to make sure that I didn't make a mistake. I want to of course, carefully plug this in the calculator as well. So, good. 84. Because sometimes you may think it is correct, but then it happens and you get a little off. So just make sure it is all same. Yeah, 84.45. So why do I do all that? I say, Alex, because you enjoy practicing. Yes, but that's not the only reason. The reason is I want to make my favorite picture of a box. And this is a big deal because what I'm going to do is produce so-called box plot based on those quartiles. What this box plot is, it's for finding outliers, the bad numbers, the numbers that should not be in my sample. That's really a big story. So if it's a first quartile and a third quartile, then based on their size, I will be able to produce so-called fences, and everything that goes beyond those fences will be my outliers. It's too far away from the sample. So fences will tell me where I need to have a cutoff for my sample elements. So if something is beyond the fence, here or on the other side, call outlier. Outlier is a wrong element in a sample that should not be there. So I just saw that 78.9 is one quartile, and the third quartile was 84.45. 84.45. So what I can do is find the range in between of these quartiles, so-called interquartile range. Interquartile range. Gap between the quartiles. Range is a really familiar name for us, right? Range. The difference between largest and the smallest, and analogously here, between the quartile number 3, you always subtract from larger to smaller, and quartile 1. So if I go ahead and subtract from 84.45 and find the difference, 78.9. So I'll use calculator for that to make sure I don't mess up. So let me do this here. So 84. This is a special procedure that is being utilized in every exercise, turns out. So we need to, well, just follow the process. It's defined to be like that. And it's all actually being proved in so-called mathematical statistics. It's the part where we take the formulas and everything for granted, basically. We don't really prove anything in this class. We just take something, and you'll see it later, and we say that's the formula we're going to use. And if one needs to know why, all I can do is refer to the definition. Like here, I must not just use interquartile range, but take 1.5. And why 1.5? Well, it's definition. It's being proved in upper level statistics sequence that you may be able to take when you decide to go to four-year schools, and that's where they have a class called mathematical statistics. So you need calculus to use for all the ideas, and it's actually not that bad, but it's three course like calculus 1, 2, and 3. So after you take in calculus 1, you can take statistics, mathematical statistics 1, 2, and 3. That's sequence of classes. And that's where they actually have a proof why this is 1.5, because students always wondering, why is it 1.5, Alex? Why don't you just take something else? But that's definition, which is actually shown very well in the upper level of statistics. So anyways, let me take 1.5 and multiply by 555. And that's it. So don't worry. That's last thing I want to look at. So that's about 8 and 325. This is going to be a big number for us in this particular exercise, because now I need to add this 835 to my right end, to my quartile. So if I moved by that 8.325 to the right, I will be able to get the fence, my right fence. And analogously, if I move from my left end of the box, which is quartile 1, by that same exact interquartile range times 1.5, it must be times 1.5, I would produce the other location for left fence. And in between of those two fences, well, everything from my sample needs to be. Otherwise, if it is further, if it's beyond fence, then I need not to use it, because that's outlier. It's going to be too far away. So what I'm doing right now is I'm adding this 3.25 with my right end. So when I add, I move to the right. So looks like we can do the arithmetic. So it's going to be 5, and then it's a 7, and it's 7. Please double check if I do it right. And that's going to be 92, right? So it's about 92. That's the right border for my sample. Looks like the sample is within. And analogously, I need to take the left end. You can, I hope, intuitively see what's going on here with this whole process when I made a picture of the box and go to the left and to the right. Okay? So and then I go ahead and subtract this 8.325 from my left end. So let's see what we're gonna produce. So I borrow 1, so it's a 9. 8 minus 3 is 5, and then 78 minus 8 is just 70. So there are two very special numbers. Fences were calculated, so my sample must be in between 70.5, which is right there pretty much, right? So the sample starts here almost on the fence, but it's fine because the lowest element is 70.9. Let's see, 70.9, where did you see? Well, my sample elements are here, my 12 elements sample. So the first is 70.9, the lowest. And my fence is actually 70.5 something. So it is almost on the fence, but it is fine because it's within the range allowed. And the other side of this sample ends at 86.2, so it isn't clearly in between of the other side. So it means that everything in our sample is good. All elements from my sample are used, should be used in my calculations. Because in a case, if I had some elements like 60 or 40 or 30, well, that wouldn't be possible. So I would need to get rid of it, because if I say you want to find the standard deviation, mean, all the stuff we did last time, it'd be giving us the wrong values because we had outliers. So somebody could have made a mistake when collecting data, or on purpose put some wrong number. You never know what happened, but this method enables us to identify those outliers without really caring what kind of elements we're dealing with. And that's very, very powerful. Please notice I didn't even worry about the story here, and that's Harry Potter story. How about that? So we say the values, um, pages, 12 randomly selected pages from Harry Potter book. So if they found those pages, whatever, and is there pages from that book, or maybe somebody by accident took page 5,000? Well, definitely we're experts in the number of pages in a textbook, and we know it's probably like maybe it's 100 pages or 200 pages usually, right? There is no page number 5,000 or 10 million. But what if it's a story about something that we have no clue what this is, and some milligram weights and the containing and the cigarettes of some kind of cotton or whatever drugs, and well, probably not many people know what those are, right? And in order to make sure that the data is collected correctly, what you're going to get is a box plot process, the one that I just introduced you with. How about that? So this box plot process is very useful in the real life situations. So they just give you a bunch of numbers and you have no idea where they got it, and you cannot check if they collected it correctly, but at least you can throw away the outliers, the ones that are too far away, using the ideas of 25%, 75%, the quartiles, range in between of them, taking time and a half, and that's how you produce borders, and that's the starting place. So it is interesting and it is very useful. And turns out that statistics is really the most useful subject related to mathematics that you learn in the college, useful in the real life, because sometimes we measure various things in mathematics in the calculus class, and students wonder and say, Alex, why do you need all that? Just to keep you employed? So we just take some tests from you, but well, it's never going to be used in my music, for example. But in statistics, we can find the problems for music majors that have a usage. I say, really? Yeah, I think we did a while ago an exercise with my other class that was showing the relationship with the lifespan of average person and the composer. So you could see if doing some music related activities has tendency to increase your lifespan. How about that? And we actually got the correct, that's increasing. It's not just amazing. On the contrary, we did exercise for medical measures. So they said that medical doctors actually have tendency to live less than the average person. Isn't that amazing? And statistics actually prove that. So if you're interested, again, you can take statistics, because that's usually being done in, I think, like chapter 8 of this textbook, the one that I shared with you. It's called hypothesis testing. You get hypothesis, you collect sample, and then you can make all kinds of inquiries and see if they're correct or not correct. Isn't that just amazing? It is useful. So for any area of real life, statistics is really being utilized. And that's why it's so exciting. And I really like this subject because that way I can answer my students' question, why we do all that. So there's no uh, doubt, I guess. But anyways, so what else can we utilize here? Well, the process of finding percents is very exciting. And I think I will try to do a couple of exercises and maybe give you a little quiz here at the end. So that way, I hope to turn on some more students eventually, because looks like we have only 3 attending, and we don't have many students in this class. I think 6 or 7. I'm not sure if it's 7 because there's, but anyways, so another half of class is not here. So I hope they will over weekend watch this recording and send me the answer for the quiz, and next time maybe we'll do a little bit more heavier work during the class meetings, because yes, the practice shows it's already week 9 of semester, so by that time week 10, 11 activity fades out and students are feeling overwhelmed, and by the week 13 they don't attend the classes, and that actually causes not to get very good grade at the semester end on the final exam. That's why it's important that now we take it seriously, right? Week 10, 11, 12. So that's what I plan to do. But anyways, I'm gonna, of course, stress it again next week. So how about if you find 10% of your sample, or 0.1, 0.10 if I multiply by 12 elements. Turns out sample size is always 12 in this particular case, and the name of this is P10, 10th percentile. You say, wait a second, Alex, you called Q1. Well, yes, you could have also used P index 25, the 25th percentile for Q1, or for your median, it could be P50, 50th percentile for the median. So we look for the percentages of sample elements, and median is 50%, half, right? And Q1, it has a special name, quartile, so they use it, but technically it's just 25%. So same here is 10%, which is 1.2. You say, wait a second, 1.2. So what should I do to take my 10%? Well, it turns out the new rule here says if you produced decimal when you take your percentile, move to the next position. And next position after 1.2, there is no position 1.2, it'd be position number 2. Since there is no position, they must select position number 2, and this is going to be here. Whatever sits in that place in my sample, it's 74. So that's your P10. You say, Alex, who told you to find P10? Well, I just created this question. Actually, later, and I think in section 2.7, 2.6 is what we skip. In 2.7, the last section of the chapter, they show those percentiles. So I'm trying to finish up with the chapter 2 today. So what I do is write down whatever sits on that second position, and that's number 74. So whatever happened to be there, just write it down. That's my answer. So you can find 10%, you can find 20%, 30%, 31%, or 21%. You can find any percentile in between 0 and 100. So let's say if I want to take 21%, I will multiply 0.21 by 12. Remember, sample size is 12 in this case, so I need to, I guess, better use calculator here, right? So let me go for the calculator and, well, and just multiply. So it's 0.21, 21%. If I multiply it by 12, I get some kind of decimal, whatever it is. I'm gonna move to the next position. Move up, people say. And that's the rule for finding percentiles. Move up and you get a place number 3, right? It was 2 something, there is nothing in the place. There is a element number 3. Okay, so element 3 is what I need to now select. So I need to take a look at my sample. It's right here. So element 3 is here. 78.6, right? So that's 21%. So I'm just making up whatever percent just comes in mind. Say 78.6 happens to be 21st percentile. Someone can say, Alex, I just tried to find 11th percentile, and it happened to be the same as 10th percentile. It happens to be, well, let's find 11th percentile. 0.11, right? Multiplied by 12 elements in the sample. Again, we keep multiplying. I say, what is that here? What is this? It's times. Let me clear this. It's trying real hard to put that little cross for the times. It looks like it's not working. I need to practice. Well, at least I have, again, access to my favorite old computer that I think is very good for the Zoom writings, because otherwise with that new one, I would just get it jumpy. And how come? Well, I've been doing so many lectures on this computer, and that's why I think it's already been rubbed down in such a way that now it really follows to what I try to put in it, and that's great. But anyways, please notice that's a decimal 132, and the rule says you got the decimal, move up to the next position. So I got the decimal 132, next whole number is 2. So we got the second position again. Please notice on the second position, first, second is number 74. That happens to be also same as the number we have on the 10th percentile. It happens to be because we don't have lots of elements in the sample, just 12. If you got more than 100, then definitely they all be different percentiles. And it's all created for, of course, bigger samples. So the whole point of study is big samples, 200, 5,000 element sample. And that's where it's all being utilized, because here it just doesn't make much difference and sense to say P10, P11, but our goal is to learn the precision. So you got decimal, you move to the next. So I'm asking you now to do a little quiz. How about if you find P90 for the quiz? So please let me know what 90th percentile is going to be. See, 90? Well, it's 10, 20, so it's probably going to be somewhere on the right side of the sample, right? So for quiz, please use analogous process. We already used number of times. And if you're not sure, well, you can do it over weekend and just email me your number that corresponds to percentile. It's no rush. In fact, I will gladly accept the emails from those students that are not here on Zoom today. So next time, I think we need to get a little bit more, I guess, maybe more extensive meeting with that. But today,
Do you want us to use the same number, 74?
I want you to find 90th percentile from this particular sample. 74 will be 10th percentile or 11th percentile, but I ask you to get 90th. So 90th percentile is definitely not the same as 10th, right? It's different. So you need to recall how we did that. So you need to look at how we find, let's say, P11s, we put 0.11 times 12 times sample size. So for 90th percentile, you need to use 0.90, right? So that's definitely going to give you something way more than 2, right? Would be, as I said, somewhere on the right side of the sample. So please take your time. Don't hurry and just put the answer in the chat or email it to me. It's also fine. Either way is fine. But again, I'm not hurrying you with this. Take your time. Okay. So it's a little quiz. We haven't had a quiz for a while. I think we should have a little bit more quizzes from now on because statistics is something interesting. So anyways, take your time. If any questions, please ask.